Hello students, I am Kausalya. Today we are going to solve example 1.9 in control systems. The problem is write the differential equation governing the mechanical system. Draw the force voltage and force current electrical analogous circuits and verify by writing mesh and nodal equations. So this is the given diagram. So as usual, our first step is we have to draw the free body diagram. So first one is free body diagram of mass m1. So as I said already regarding m1, just count the number of elements which are connected with m1. So here we have 1, 2, 3. You have to consider force also, 4. So totally we are having 4 elements which are connected with M1. So totally while drawing free body diagram, we will be having 5 forces totally, right? So the first one is applied force F1 of T. So I have drawn already. This is your applied force F1 of T. So the opposing forces are provided by the rest of the 4. So the first opposing force is provided by Fk1. So write it as. Then the second opposing force is produced by B1. So that is Fb1. Third opposing force is produced by this K2, Fk2. Apart from these 3 elements, an opposing force will be produced by our mass M1. So the opposing force produced by mass M1 is Fm1. Right. Totally we are having 5 forces. So just write down the expression for each force. So the first one is Fk1. So Fk1 is directly proportional to the displacement. This is nothing but x1. So Fk1 is equal to k1 into x1. Right. And the next force is Fb1. Again Fb1 is directly proportional to dx1 by dt. So here when you include proportionality constant, that becomes b1 into dx1 by dt. And the next one is Fk2. Here again this K2 is connected between masses M1 and M2. So while writing Fk2 is directly proportional to, here we are considering mass M1. So we have to consider the displacement of mass M1 first. So we have to write it as x1 minus x2. So x1 minus x2. So when you include proportionality constant, that becomes k2 into x1 minus x2. And the last one is Fm1. So F1 is directly proportional to d square x1 by dt square. So which is equal to m1 into d square x1 by dt square. Right. Now by Newton's second law, that is in Newton's second law, force will be expressed as mass into acceleration, right? So by Newton's second law, here we are writing the applied force F of t is equal to opposing forces. So here the opposing forces are Fk1 plus Fb1 plus Fk2 plus Fm1, right? Just substitute the values accordingly. So Fk1 is nothing but k1 x1 plus Fb1 is b1 into dx1 by dt plus Fk2 is k2 into x1 minus x2, and last Fm1 is m1 into d square x1 by dt square. Right. Hope you all are clear with this. We have solved lot of problems like this before. And the next one is here I am going to rewrite displacement x in terms of velocity v. Right. So when you rewrite, the above equation will become, that is writing f of t expression in terms of velocity. Right. So when you write, you will be having f of t is equal to k1. Here x1 should be written as integral of here x1. So here I am writing it as v1 into dt plus again b1 into dx by dt is nothing but velocity v. So here dx1. So I am writing it as b1 v1 plus again k2. So k2 is into integral of v1 minus v2 into dt, plus finally m1 into d square x by dt square is nothing but dv by dt. So here it is d square x1. So here I am writing it as dv1 by dt. Right. Name this expression as expression number A. Right. Then the next step is we are going to draw free body diagram for M2. So this is our free body diagram of M2. So regarding this one, again from the problem, just count the number of elements which are connected with M2. So to this M2, we are having 1, 2, 3, 4. So apart from these 4 forces, we will be having another one opposing force produced by this mass M2. So this free body diagram will consist of totally 5 forces, right? So here F2 of T is the applied force and the remaining forces are produced by Fk2, Fk3, Fb3 and finally Fm3. Again we are going to write the equivalent expressions here. So when we write, we will be having Fk2. Again Fk2 is connected between your masses M1 and M2. Now we are considering M2. So the displacement of M2 is x2. So we have to write x2 minus x1. So Fk2 is directly proportional to x2 minus x1. So when include proportionality constant, that becomes k2 into x2 minus x1. And the next one is Fk3. Here again this k3 is connected between M2 and M3. Now I am considering M2. So the displacement of M2 should return first. So we have to write x2 minus x3. So again Fk3 is written as x2 minus x3. When you include proportionality constant, that becomes k3 into x2 minus x3. Right. And the next one is Fb3. Again this Fb3, that is B3 is connected between M2, M1. So initial displacement, that is x2, we have to write it as x2 minus x3. So Fb3 is d by dt of x2 minus x3. So when you include proportionality constant, this one becomes, which is equal to B3 into d by dt of x2 minus x3. And the last one is Fm3. So as we all know, the opposition force produced by mass is directly proportional to acceleration. So this will be Fm2. So Fm2 is directly proportional to d square x2 by dt square. Again when you include proportionality constant, that becomes m2 into d square x2 by dt square. Right. So again by Newton's law, applied force will be equal to opposing force. So here we are having an applied force F2 of T. F2 of T is equal to Fk2 plus Fk3 plus Fb3 plus Fm2. Okay. You just leave this one. Just substitute the respective values. When you substitute for Fk2, that becomes K2 into x2 minus x1 plus K3 into x2 minus x3 plus B3 into d by dt of x2 minus x3 plus m2 into d square x2 by dt square. This is your applied force F2 of T. Right. Again, I am going to replace this displacement in terms of velocity. So when you replace, your expression will become F2 of T is equal to K2 into integral of x is represented as integral V. So here V2 minus V1 into dt plus again K3 into integral of V2 minus V3 into dt, and here B3 into dx2 by dt is nothing but V2. So V2 minus V3, and finally M2 into d square x by dt square is nothing but dv2 by dt. This is your expression number B. Right. And the next step is I am going to draw free body diagram of our mass M3. So when you consider, when you look at this, when you look at the problem, here I am having this mass M3, just count the number of elements connected with mass M3. Here I am having 1, 2, only 2 elements which are connected here, and there is no direct force applied on this mass 3. So totally only opposing forces will be present here and 3 opposing forces. So the 3 opposing forces are namely Fm3, Fk3 and Fb3. So again just write down the respective expressions. So when you write, we will be having Fm3 is directly proportional to the, here the respective displacement of M3 is given as x3. So d square x3 by dt square. So when you include proportionality constant, that becomes M3 into d square x3 by dt square. And the next one is Fk3, and this Fk3 is connected between M2 and M3. Now we are drawing free body diagram of M3. So we have to consider this displacement x3 first. So we have to write it as x3 minus x2. So Fk3 is directly proportional to x3 minus x2, which is nothing but k3 into x3 minus x2. The last one is Fb3. Again this Fb3 is connected between M2 and M3. Again the initial displacement should be considered as x3 as we are drawing free body diagram for M3. So here that becomes Fb3 is directly proportional to d by dt of x3 minus x2. So which is nothing but b3 into d by dt of x3 minus of x2, right? Again by Newton's law, just I have to write applied force equal to opposing force, right? So here there is no direct applied force over here. So applied force is 0, which is equal to Fm3 plus Fk3 plus Fb3. Just substitute the values here. We will be getting M3 into d square x3 by dt square plus k3 into x3 minus x2 plus finally b3 into d by dt of x3 minus x2. Again here I am going to rewrite this expression in terms of velocity. So here we will be having 0 equal to m3 into, so d square x by dt square is nothing but dv by dt. So here it is 3. So here I am writing it as dv3 by dt plus again k3 into integral of v3 minus v2 into dt and finally b3 into v3 minus v2, right? Name this expression as expression number C. So here we had solved only our first step, that is the differential equations governing the mechanical system had written, and the differential equations are respectively, this is your first differential equation, equation number 1, and F2 of t equal to, this is our second differential equation, and here this is our third differential equation. And the next step is, now we are going to draw the force voltage and force current analogy. So for drawing this force voltage force current, we should have these expressions, that is expression in terms of velocity. So here I had written all the 3 expressions which we had got from the 3 free body diagrams. So from this diagram, the first step is I am going to draw force voltage analogous circuit. So I had made a special video on this force voltage and force current analogous circuit. Those who are watching this video as first, it is must for you people to watch that video so that you can have a clear idea, right? I'll give the link in the description. So here regarding this force voltage analogy, this force will be equal to voltage. We are having 2 forces, right, from the free body diagram. So F1 and F2. That becomes E1 and E2. And similarly, V1 becomes I1, V2 becomes I2, and V3 becomes I3. And these masses will be represented as inductors, and this dashpot will be represented as resistors, and this spring will be represented as a capacitors, right? So here in this equation we are having three velocities v1, that is v1, v2, v3. So here I had written 3 and we are having 3 masses, right? m1, m2, m3, and here I had written these 3 masses. Then apart from that we are having dashpots b1 and b3. So I had written b1, b3, and the last one I am having 3 elements, k elements. So k1, k2 and k3. Now we are going to draw the force voltage analogous circuit. So just observe carefully. So consider your first expression, right? So in this first expression you are having a force F1 of t. So this F1 of t is now represented as E1 of t, right? So the first one is, here I am drawing a source voltage and this source voltage is E1 of t. So not alternating, plus minus, right? So just draw that one. And the next one is, we are having a mass M1. This mass M1 should be represented as an inductor L1. So just draw an inductor here. Okay, this inductor is your L1. And the next one is, we are having a B1. This B1 should be represented as resistor here. So just draw a resistor, and this is nothing but this is your R1, right? And the next one is, here I am having a K1. So this K1 should be represented as a capacitor. So here I am writing it as a, I am drawing a capacitor here, that is represented as a C1, right? Then the next one is, here I am having a K2, and that K2 is between V1 and V2. Okay, that is between your first loop and second loop. So here K2 should be represented as C2. So just I am drawing a C2 here. Right, this is your C2. That's it. Our first loop gets over here. Right. So just count the number of expressions here. Sorry, number of elements in the expression. 1, 2, 3, 4, 5. Totally you should have 5 elements in your first loop. Again 1, 2, 3, 4 and 5. Right. Hope you all are clear. And again the current flowing through this first loop should be represented as I1. Now consider our second expression. In second expression again I am having a mass M2, and that M2 should be represented as an L2. So just draw an inductor here. It is your L2, right? And the next one is, we are having common elements, right? V2, V3, V2, V1, V2, V3. Okay, these are all common elements, so just leave it. And again we are having a F2 of t, and this F2 of t should be represented as another voltage source. So just draw another voltage source. This is nothing but your E2 of t, right? Right? And now we are going to draw the common elements. So regarding common elements, here you listen. We are having a B3 which is between your second loop and third loop. So B3 is nothing but here R3. So just draw a resistor R3 here. So this is your resistor R3. And the next one is, here we are having a K2. This is common for second and first loop, and this K2 is represented as C2, and this C2 we had drawn already. So we can leave it. The next one is, we are having K3. This is between your second loop and third loop, and this K3 is again a capacitor. So just again draw a capacitor, and this is your capacitor C3, and this is our loop 2, right? And I2 is the respective current flowing through the loop 2. Again just count the number of elements. 1, 2, 3, 4, 5. There are 5 parts in an expression, and again here 1, 2, 3, 4 and 5. 5 elements in our loop 2, right? And the next one is, we are having mass M3. So M3 is represented as L3. So here just draw an inductor L3. And we are having B3, and B3 is nothing but R3 which we had already drawn. And the next one is K3. K3 is nothing but C3 which we had already drawn. And that's all. Our loop 3 gets over. Our loop 3 consists of only 3 parts, 1, 2 and 3. And similarly here also we are having 3 elements, 1, 2 and 3. And let I3 be the current flowing through this loop, right? Hope you all had understand this one well. If you have any doubt, let me know in the comment section. Now we are going to write the mesh equations. So mesh equation is written by applying Kirchhoff's voltage law. So Kirchhoff's voltage law is nothing but sum of voltages in a closed loop is 0. So here in this case, this is your supply voltage. So E1 of t, that is KVL at loop 1, right? So E1 of t is nothing but this source voltage is equal to voltage drop across the respective elements. So the voltage drop across the element is nothing but L1 into di1 by dt plus I1 into R1 plus again voltage drop across the capacitor is given by, it is nothing but 1 by C into integral of I1 into dt plus again voltage drop across capacitor C2 is 1 by C2, and again this is connected between the loops 1 and 2. So here I am considering loop 1, right? So I have to take I1 as first. So 1 by C2 integral of I1 minus I2 into dt. Okay, this is your expression for your loop 1. Right, totally 1, 2, 3, 4, 5. 1, 2, 3, 4 and 5. Just respectively check whether each and everything is correct then and there. Right. The next one is I am going to write expression for loop 2. So again in loop 2 I am having a voltage source, right? So that voltage source is E2 of t. So this E2 of t is nothing but, here we are having L2. So L2 into di2 by dt, because current flowing through this loop is I2. Plus again we are having R3. So voltage drop across R3 is connected between loop 2 and loop 3. Now I am considering loop 2. So current flowing through loop 2 should come first. It is nothing but I2 minus I3 into R3. Right. Plus again voltage drop across the capacitor is given by 1 by C3 into integral of I2 minus I3 into dt. Right. Plus here we have written inductor, this voltage source, this one, and the remaining left is this capacitor. So this is nothing but 1 by C2 into integral of I2 minus I1 into dt. Right, because this C2 is connected between 1 and 2, and the current flowing through one is I1 and second one is I2. As we are considering our second loop, we have to write I2 first, that is I2 minus I1. Right, and again just apply Kirchhoff's voltage law to your loop 3. So when you apply it to loop 3, there is no source voltage. So the source voltage is 0, and you have to write the respective voltage drop across each and every element. So L3 into di3 by dt plus again 1 by C3 into integral of I3 minus I2 into dt plus again I3 minus I2 into R3. Right. So totally we are having 1, 2, 3 elements, and our expression should consist of 3 parts, 1, 2 and 3. Right. So this is the respective force voltage analogous circuit, and these are the respective expressions. Hope you all are clear with this. Shall we move to our force current analogy? So this is our force current analogous circuit. Okay, again these are all the first expressions A, B and C, that is expressions in terms of velocity. So here from these expressions again by the force current analogy circuit, that is the force will be represented as current, and voltage will be represented as same voltage, and masses will be in terms of capacitors, and this dashpot in terms of resistors, and spring as inductors. Right. So these are all the things we already know. I had made a separate video in this, you can watch. And the next one is, instead of drawing a circuit with respect to this one, I will tell you how to draw a force current analogy from your force voltage analogous circuit. This is quite simpler and easier, right? So the first step is, the thing which you have to keep it in mind is, the elements which are represented in series here, they will come as parallel in our force current analogy, and your voltage will get converted into current. That's it, nothing more than that. And here the thing is, that is what to say, the value of your, that is the position of your inductors and capacitors, that is L2 inductors will be represented as capacitors, and capacitors will be represented as inductors. Only three things you have to keep it in mind. So the first one is the elements which are connected in series should be represented in parallel, and the second one is the voltage source will be represented as a current source. Okay, and the third one is inductors and capacitors will interchange. That is, inductors should be represented as capacitors and capacitors should be represented as inductors. That's it. Right. Shall we proceed now? So the first one is, here I am having a voltage source. So this voltage source is converted as a current source. So here I am writing it as I of t. And to this current source we are having this inductor in series. So inductor should be replaced by capacitors here. So here this L1 is represented as a C1. Right. And again you see this R1 is in series with L1. So again I have to draw an R1 which is in parallel with this C1 here. So here I am having my R1. And the next one is I am having a capacitor. As I already said, the capacitor should be replaced by a inductor. So just draw an inductor, and this inductor is L1. Right. So these four elements are in series. Now I have drawn these four elements in parallel. Okay. Inductor should be represented as capacitors, and this capacitor should be represented as inductors. This is the main key point. You have to keep it in mind. And again the next one is, here I am having a capacitor, and this capacitor is common. This lies in the path common for loop 1 and loop 2. So the elements which are common and which are parallel should come in series. So this C2 should be represented as an L2 here. Right. And the next thing is, so this forms our node 1. And the next is, we are having a voltage source. So this voltage source should be again represented as a current source, and this voltage source is again in series. So here I am drawing it as parallel, and this is nothing but your I2 of t. And next I am having L2 in series with this. So L2 should be represented as capacitor, and here the series element should be represented as a parallel element. Here this is nothing but C2. Right. And the next one is, here again these two elements are in series, and these two elements are common for loop 2 and loop 3. So the series element should be represented as parallel. So when you represent it as parallel, here this resistor R3 comes as such. This is your R3, and this C3 should be represented as inductor. So here I am representing it as L3. Right. And the last one is, we are having an inductor, and this inductor should be represented as a capacitor, and this forms your C3. Okay, this is your node 1, and this forms your node 2, and here this region forms your node 3. Right. So in the first loop 1, 2, 3, 4, 5, and here to the first node you should have again the 5 elements 1, 2, 3, 4 and 5. Right. To this in this loop 2, 1, 2, 3, 4, 5, and here again in this node 2 we should have 5 elements which connected. So 1, 1, 2, 3, 4, and here this one also. Okay, this is common for your node 1 and node 2. So 1, 2, 3, 4 and 5. And to this loop 3 we are having 3 elements. So 3 elements should get connected. That is 1, 2 and 3, which are connected to your node 3. Right. Now we are going to write the expressions, that is the respective expressions here. So when you write the expression, we should represent this node 1, node 2, node 3 as a potential V1, V2 and V3. So while writing nodal equation at V1, when you write, so the equation will become I1 of t is equal to current flowing through the capacitor is given by C1 into dV1 by dt, and current flowing through the resistor is given by V1 by R1, since everything is connected to V1. And the current flowing through the inductor is given by 1 by L1 into integral of V1 into dt, and again the current flowing through this L2 is given by 1 by L2 into integral of V1 minus V2 into dt, because this L2 is connected between node 1 and node 2. This is our first nodal equation. And when you write for this V2, So that becomes, here again we are having an current source. So I2 of t is equal to, again current flowing through this capacitor is given by C2 into dV2 by dt, plus again we are having this L2, right? So for this we have to write it as 1 by L2 integral of V2 minus V1 into dt, and the next one is plus, we had written this one and this one, we have to write these two expressions. So R3. So in this R3 we have to write it as V2 minus V3 by R3, plus again the current flowing through this L3 is given by 1 by L3 into integral of V2 minus V3 into dt. This is our nodal equation for node 2. And the last one is at node 3, that is at V3 we will be having, there is no direct current source, so I am writing it as 0. So this 0 is equal to V3 minus V2 by R3, plus again 1 by L3 into integral of V3 minus V2 into dt, plus and the current flowing through the capacitor is again C3 into dV3 by dt, right? So this is our nodal equations. That's all, our problem gets over here, right? This problem will be quite easier when you are solving more number of problems like this. And I hope this is the lengthiest video I have made. Yeah, the problem gets over here. Thank you. If you have any comments, let me know in the comment section. If you have any doubts or you need any clarification, feel free to ask. That's all. Thank you.